of summation, let's take a look at that. What you see here is a graph, actually two graphs superimposed upon one another. The first graph compares the membrane potential of the skeletal muscle fiber and time. If we take a look at the action potential then that is generated, we can see this action potential. Actually, let me switch to highlighter. We can see this action potential here. The hyperpolarization phase suggests that it's a neuron, but it's actually meant to represent the action potential of the skeletal muscle. So this would be the muscle cell depolarizing and then repolarizing, generating an action potential. And that action potential then is going to travel down the T-tubules to trigger the release of neurotransmitters. Now, if we follow this action potential, if we look at this action potential and we start at the peak right here and follow it down, whoops, to the best of my ability to make a straight line, to my time, okay, about right there, I guess will work. This is the time at which the peak of the action potential occurs. Now, the next graph that we're looking at, it's placed right on top, is a graph where we measure force. Now, this force can also be tension. It's essentially the same thing, so sometimes you might see a graph that says tension instead. And we don't really know the units. It could be pounds per square inch. That's the measurement system in the United States. It could be kilograms per meter, I guess, or grams per meter. It's some unit of force. And so we don't know the exact value, and that's okay. But if we look at the shape of this contraction, and we have our contraction phase of the muscle twitch, and then our relaxation phase of the muscle twitch. And this, again, we can kind of pick the middle of this as best we can and follow this down. So here's the peak of my force that's generated. So this is my force curve or tension curve over time. And we can compare the difference. You'll notice that there is a difference between, if I compare from here to here, you can see that there's a delay. The peak of the action potential occurs substantially earlier than the peak of the muscle twitch. And essentially the time that it takes for the action potential to occur and then for the muscle fiber to begin to generate force is referred to as the latency period. That latent period, the time between the action potential and the generation of force. Now, the latent period technically would be somewhat small. It's really essentially just this section right here between the peak and when we start to generate the force. But I like to look from peak to peak because I think it's easier to see. This process of latency is due primarily to simply the time that it takes for the action potential in the skeletal muscle to lead to calcium release, and then for that calcium to bind troponin and initiate contraction. And that takes time. So the action potential, of course, occurs first. These are the processes that must occur during that latency phase or that latency period. And then we finally get the buildup of force. And again, it's an ongoing process. We start with just a few myosin cross bridges, and then we continue to build tension as the sarcomers shorten in length until we get to our maximum tension. Now, the contraction relaxation phase, let me zoom in on this for you, is one contraction, one relaxation is referred to as a muscle twitch. And this muscle twitch will occur. Now, let's imagine, so I want you to think back to the neuromuscular junction, and you'll remember me talking about the importance of threshold, right? If we reach threshold, we're going to get an action potential in the skeletal muscle fiber, and that will lead to calcium release. If we create a much bigger graded potential, the action potential is still the same size, okay? And it's going to generate a muscle twitch. Now, so that muscle twitch from one voltage that is threshold voltage, and so here's the stimulus. This is going to represent the action potential here, okay? And actually in this figure it would be an electrical stimulus similar to what you used in lab, but it will represent the action potential. So let's kind of follow this up. Notice this delay period here. I need a smaller pen. From here to here, technically that's the latency period. And then if we look at the delay between the peak, I think that that is an important period to follow as well. And I'm going to follow it all the way down to here. Okay, and I'll explain that in a minute. So contraction phase, that's this upward sweep right here, followed by the relaxation phase. Notice the relaxation phase is longer. It takes longer for us. This whole phase is due to that calcium ATPase working its butt off to put the calcium right back where it belongs in the sarcoplasmic reticulum, but that's a slower process than the release of calcium.
Can I tell you some bad news?
Okay, so now the thing that we're going to look at here, this is just due to one stimulus. So one action potential that it reaches threshold one graded potential reaches threshold voltage, generates an action potential in the skeletal muscle membrane, the plasma lemma or sarcolemma, and then we get our twitch, contraction, relaxation. So release of calcium, buildup of force. Now, what happens though? Okay, now if I get, let's look at this. We're going to continue with this drawing. Let's pretend I get another action potential right here. What does that do? Well, if we wait for our latency period to occur, and I'm going to try to estimate the same size. Well, we're going to get an action potential. I'm sorry, we're going to get we're going to begin to build up force here, and then a relaxation phase here, and we have another twitch, and it should look about the same. If I had better drawing skills, it would look exactly the same. And so we would essentially get two twitches, two individual muscle twitches in a row. But what if instead we get an action potential right here? That action potential would hit, let's follow this up, before the muscle has begun to relax. And so if we allow for a latency phase, you'll see that the latency occurs even before the peak. So at this point, we're going to begin to, let's kind of estimate this up, right about here, we're going to begin to build up force. And we end up adding the force that we are now generating because of the new action potential on top of the force generated by the old action potential, or the previous action potential. And so now our muscle twitch is bigger. And we call this summation, and it's actually not one twitch, but it's two twitches added on top of each other. And so that's the summation part. If we look at this down here, this is what it looks like if you had a better artist. And so you can see in this case, here's my stimuli, one stimuli here. Let's follow it up. There's my latency period right there. Another stimuli here, follow that up. And then a latency period here before the muscle has completely relaxed. And so we end up with this summation process. Now, summation is important in terms of increasing muscle strength. This is one way of increasing strength. Not strength of the muscle, sorry, force. The force being generated. This is one method. Another method is the number of cross bridges, which we talked about previously. The more cross bridges we form, the stronger the contraction. Another way is how much we shorten that sarcomer, which is directly dependent on our starting muscle length. But this increasing in force, let's kind of look more on that. So how do we do that? Well, it has to do with the frequency of action potentials generated in that skeletal muscle fiber. The higher the frequency, the more summation we get. So continuing with my bad drawing, let's imagine, let's erase some of this noise so it's a little easier to, whoops, not what I wanted. All right, bye-bye. So we get a little bit easier. And my next action potential was what, right there? If we get another one, let's say right here, we're going to repeat this process. So again, if we assume a latency period between here and here, and we follow that up, we're going to start contracting again right here. And so now we're going to build, once again, adding one twitch on top of another, like so. And then if I add another action potential, again, more force. Sorry, ugly twitch. But you can see that I'm increasing the force that is being generated by increments. Now I will eventually reach a point at which I can generate maximum force. So what does that look like? Well, maximum force, so all of this, by the way, is summation. This is summation right here, which is the two twitches adding on top of each other. This is summation here, where we're adding multiple twitches here. This is summation, and this is summation. All of this is summation. But when I reach a point at which I can generate maximum force, so we reach what we call tetanus. Now there's two types of tetanus that we need to be aware of. One is called incomplete or unfused. And here we're not truly at our maximum force, but we're getting there. We're kind of getting close to there. But what you actually see is this relaxation that occurs in between twitches. There's a slight relaxation, but you'll notice that we get a plateau right here. And so if I were to do an average value there, my force essentially plateaus at whatever this value here is going to be. And that plateau indicates we've reached tetanus. And because of the relaxation periods in between each peak, it's called the incomplete tetanus. We can get an even greater generation of force and still have it be incomplete. If we zoom on it here, even though it's not super obvious, we do still see a little bit of contraction, relaxation, contraction, relaxation, contraction, relaxation, and so on and so forth. And so anytime we have it, even if it's a very brief amount of relaxation, it's considered unfused or incomplete tetanus. But of course, the force that we generate is a little bit more. And so we've created maximum force in the muscle fiber. Now, complete tetanus, there's no time for relaxation. It's here. You'll notice once again, we've increased the amount of force that can be generated. We are now in complete tetanus. We are at our maximum possible force that those particular muscle fibers can generate. Now, muscle cannot remain in its complete tetanus for long. Eventually, we're going to start to see a decrease in the amount of force generated. We call this muscle fatigue. Let's take a look down here. You'll notice here is the length of the stimulus. So what we're receiving here is constant action potentials, one right after another. They'll actually blend together to look like one solid little line, but they continue all the way to the end, never stopping. So even in this period here, we're still receiving a high frequency of action potentials. And of course, that frequency is measured in hertz. And so while the action potentials might continue, we're fatiguing. And what's happening there is that we're depleting our ATP sources. Carbon dioxide is building up in the muscle tissue and surrounding areas, which is converted into acid. Actually, it makes acid plus bicarbonate ion. But it's the acid that is creating problems because it's going to change the pH of the surrounding environment. Let's get rid of the crazy size. In addition, we've got some we're assuming, so our oxygen levels are going down. And we assume that that means some of the pyruvate that is being generated will be sent to the lactic acid cycle. And so we're probably building up some lactic acid. And there are other metabolites and so forth that will accumulate in these working skeletal muscles that lead to fatigue, but these are the big ones.